Okay, so I need to talk a little bit about what the ideal gas law is. One of the things you've learned previously is that when we think of volume of a gas and its pressure, if you change the volume of the gas, the pressure will change as well, but they're inversely related. So if you increase the volume of a gas, the pressure will go down. Here, you're holding the moles and the temperature of the gas constant. We've also learned about Charles' law in that the volume and the temperature of gas are directly proportional. You increase one, you increase the other. In this case, you would have to keep the moles and the pressure of the gas constant. Avogadro's law is the relationship between the volume and the moles of the gas, and so they are directly related. Again, increase one, increase the other. Avogadro's law applies when you hold pressure and temperature constant. Now, if you wanted to, you can sort of combine these proportionalities into one equation, and so I've done that there. And you can see that volume is going to be directly proportional to moles, which is N, and temperature, but inversely proportional to pressure. And so one of the things that you already know is you can take that proportionality between volume and NT over P and turn that into an equality if you add some kind of numerical constant. So I've done that there. Here I say V is equal to constant times NT over P, and now we're not going to call the constant K anymore. We give it a special letter. We're giving it a capital R. So V is equal to R, which is the constant, times N times T divided by P, and then you can sort of rearrange variables, and then we sort of get the common expression of this new gas law we're going to deal with, which is PV is equal to nRT. This law is called the ideal gas law. So the thing to sort of note about the ideal gas law is it's a little bit different than the gas laws you sort of used in the past. With the gas laws you used in the past, usually in the problem what you would have is you would have some initial conditions, and then what you wanted to do was define a property of the gas maybe at some new conditions. But here it's a little bit different. Here we're just looking at a gas at the same conditions. And here within those conditions you may be given, say, three properties. For example, you might be given, say, a volume or moles and temperature of the gas. And from those properties at those conditions, you just find the pressure. Now, one of the things you need to worry about is the value of R. And so that will be given to you on a test. But just to note that this constant, this R, which is in that equation, can have different values depending on what the units are going to be in that equation. So for example, if you're given a volume in liters and you're given a pressure in atmospheres and you have moles and a temperature in Kelvin, R would be equal to 0.08206. However, in a problem, if you were given a volume not in liters but in milliliters, but you had atmospheres in Kelvin, then R would be a different value. It would be 82.06. You might, instead of having pressure in atmospheres, you might have it in a different unit like kilopascals, and then R changes its value again. And so there are all these different values of R depending on what the units are for the properties of the gas. And so the best way to sort of deal with that in a problem is probably just use this first value of R, which will be given to you on a test, which is 0.08206 liters atmospheres over moles degrees Kelvin are the units for the constant. And so if you are given a problem, you can use that value of R if you take each of those properties of the gas and make sure they are in the appropriate units that you see there. So volume must be in liters, pressure must be in atmospheres, and temperature must be in Kelvin. And then there's going to be some kind of amount of gas which will hopefully be in moles. So let's go ahead and do a practice problem given that information. We have sulfur hexafluoride is an odorless, colorless, very unreactive gas. Calculate the pressure in millimeters of mercury exerted by 1.82 moles of the gas in a steel vessel at 5.4 liters at 72.5 degrees Celsius. Okay, so let's go ahead and assign some variables here. We're going to try to find the pressure of the gas. So I'm going to put a question mark here. We have the number of moles of the gas, which is 1.82 moles. And so it's contained in a vessel, and so the volume of that vessel is 5.40 liters. And then the temperature of the gas is 72.5 degrees Celsius. So I think what you can sort of see with this problem is we have initial conditions here, but we don't have new conditions that we're converting this gas to. We're looking at the initial conditions, and given we know the moles of the gas, the volume of the gas, and the temperature of the gas, can we find the pressure of the gas? And the answer is yes, we can using the ideal gas law. And so the pressure here is P times V is equal to nRT. And so we can solve for P using this law. And so R, let's just write this out, it's 0.08206, and the units are liters, atmospheres, over moles, degrees Kelvin. So what we have to do to use this formula is we have to make sure that we have all these properties in the correct units. So volume is in liters, which is good. We have an amount of gas in moles. We will have to convert this temperature into Kelvin. So it's going to be plus 273.15. And again, I'm going to use that trick that the book does where we work out what the temperature is in Kelvin by adding 273.15 and then rounding it at this point to the correct number of significant figures, plus 273.15. And so I get on my calculator 345.65, but note the uncertain digit in 72.5 is here, the uncertain digit in 273.15 is here, and so here I think this is going to be 345.7 rounded to the correct number of significant figures, and this is in degrees Kelvin. Okay, so at this point what we can do is we can plug this into the ideal gas law. But first, let me go ahead and solve this for P. So you can work it out on your own, but P should be equal to nRT over V. Okay, so let me go ahead and just plug in numbers here and see what we get. N is going to be 1.82 mole. R is 0.08206 liters, atmospheres, over moles, degrees Kelvin. And then, let's see, the next thing we need to have is T, which is 345.7 degrees Kelvin. And then what we have finally is volume, which is 5.40 liters. And so let me just confirm that the units cancel as expected. So moles here cancels, liters cancels here. We have an Kelvin cancels, and so we're left with atmospheres in R. And so when we plug in these numbers, we'll get a pressure in atmospheres, which we'll have to convert into millimeters of mercury. So let's go ahead and work that out. So it's going to be 1.82 times 0.08206 times 345.7 divided by 5.4, and I get for a pressure 9.56. I'm going to round this to correct number of significant figures at this point because that's what the book does after you plug in numbers into the equation. So there should be 3 significant figures. So I get 9.56 atmospheres. Now that's not the answer. We really had to convert this into millimeters of mercury. So I'm going to multiply it by 760 millimeters of mercury. I think these 3 digits are considered significant. Over 1.0 atmosphere. 1 is an exact number. And so what do I get? I get times 760. And so I get, rounded to the correct number of significant figures, I get 7270, should be 3 significant figures, millimeters of mercury. And if you wanted to, you can convert this into scientific notation. So that should be the answer there. Okay, so let's move on.